Okay. Well, thank you for being here. Today we are going to be talking about Taylor series and approximations. And as I was saying, as some people are coming on, I really am going to kind of go slow, go kind of like back to basics, really think about those foundations, and try to solidify like why we even talk about, like why do we care about these things called Taylor series, and then sort of build up the knowledge from there. I was talking to Stephen yesterday at office hours that I do feel bad that like our learning around series in general has been so interrupted and piecemeal. It definitely was definitely difficult as a calculus teacher to get word that basically like there's 5 topics from series that are being assessed this year, because it's one of those topics that I know I used the analogy earlier this week, like how do you tell somebody, for example, that like we're going to learn how to divide fractions and then tell them, but we're not actually going to teach you how to multiply integers or multiply fractions and do all that stuff, right? It's hard just to like teach a more advanced skill and eliminate these other things. So I know at times my discussions have roped in things that are not in the test, because it's been an attempt to try to help your knowledge be a little stronger, to have all those tools instead of trying to teach you something siloed off. For today, though, I am going to back up a little, sort of go through the foundations of why we care about Taylor series, connect it to some of the things that are important, that we have learned so far in reviewing and just learning in general on Unit 10 series related stuff, and give us a chance to practice a little bit, okay? There was a request also that I got in an email today to make sure that I post all of the lesson for today, the AP Review 14, post those answers today so that people can check before they take that practice exam, that I emailed out. If someone didn't get it, please let me know, because someone told me they didn't actually receive my practice exam. But I want to post the lesson 14 answer so you have a chance to check those things before going into the practice exam. Please do read my instructions carefully for that practice exam, because they're a little different this time. I'm trying to make it a little closer to the actual exam, so do read that carefully. It involves also some texting me, but all that stuff needs to be done by 12:30 tomorrow, because at 1 o'clock during our live session, I would like every person there, because we're going to be going over a couple really important things. One is like exam day processes. Now that I have more information, I was on a call with Trevor Packer and some other test leads earlier this week. We're going to go through some of that stuff for the first 20 minutes. The AB calculus students will join us. And then after that, we're actually going to score this practice exam, sort of see where we are at now, okay? Any questions on any of that going through your minds before we start? If there are, you're welcome to just drop them in the chat along the way. All right. So let's go ahead and get started. Okay. Here we go. Let's build up from the beginning, okay? Sometimes it's good just to build that foundation over and over and over again. All right. So we're going to be talking about Taylor series and approximating functions using Taylor polynomials. So I want to first start off by just thinking for a little bit about like, why do we even care about this thing that we call Taylor series, right? And how does it connect with the other series stuff that we've learned? So here we go. Let's back up. A series, as we know, is really just a sum of stuff. And it turns out that we can make series sums that are infinite. They just keep adding things. And they essentially fall into 2 categories, if you will. I'm going to kind of write this over on the side for now, just as we review some things. That a series is a sum. Wow, that's a thick pen. A series is a sum. And series break down into kind of 2 situations. There are convergent series. A convergent series means it goes to a finite sum. Think of them as finite. They're an infinite series, but the sum is finite. Oh, finite sum. And divergent series, which means it sums up to some infinite thing. An infinite sum. And it turns out mathematically that convergent series are really, really powerful tools for mathematics. Even even through all the jobs and stuff that we have as engineers and things this year. Before school closure, Dr. Zarin and I had actually planned on having her come and do a little mini lesson about Taylor series in engineering, because she essentially has a whole course that she took about engineering that is essentially all Taylor series, and the usefulness of Taylor series for engineering work. So these convergent finite sum series, turns out they're really, really useful. And these convergent series, we can really root them in the simplest of all of our series in a lot of ways. We can root them in geometric series. Geometric series, right? Geometric series, we've seen those. Those are series that have a very basic pattern where we're adding things that are multiplying, that each term in the sequence is some multiple of the previous one. Things like this, right? Oh, this must be an ellipsis. Plus 1 over, this would be 3 to the n power, right? So these geometric series we have seen, these geometric series have a general form. The series would be from 1 to infinity of some original a, some like starting value. In this case, it was 1. R to the n. This is our general form of a geometric series, and this specific series I started to write out over here, it would look like this, right? It would be the sum from 1 n equals 1 to infinity. N equals 1 to infinity of, our starting term was 1, so a will be 1. My r value I multiply by each time is 1/3. So this would actually just be the series of 1/3 to the n. That's what I wrote out over here. This is a geometric series. Now we know that geometric series, they converge. They converge in very specific situations, right? A geometric series converges if, let's connect that over here to what we just said about convergent things. A geometric series converges if the absolute value of r is less than 1, right? I go, well, Mark Walter, why are you bringing all this stuff up? How does this connect with Taylor series? Here's the connection we can start making. We know that geometric series converge. There's a finite sum if the absolute value of that r value is less than 1. And we know that it sums to a over 1 minus r, right? Okay. So let's think for a second. Let's imagine a series like this that I've written down on your paper that is what we call a power series. We call this a power series because n is our power. X, the variable thing here, is the base. An exponential thing would be like n to the x. A power thing is x to the n. Okay. So we have this power series here. And I'm going to say it's equal to 1 over 1 minus x. I go, well, wait a minute, that looks very similar to the sum of a geometric series. And that makes sense because really over here we can think that this a value is 1. So I didn't write it, which is why my numerator up here is 1. I'm going to, this is going to be 1, my initial a value, over 1 minus x. This is only going to be true, right, in certain moments for x, for certain values of x. Someone can either type in or like open up the microphone. For what values of x is this equation actually going to be true? What values of x would this summation actually equal 1 over 1 minus x? For what x values do you think? What values of x could I sub in here so that that number to the n, so remember I'm saying the absolute value of x is less than 1. I like that. So let's actually think about it this way, right? This 1 over 1 minus x is the sum of a geometric series, right? We know that it fits that pattern, which means, well, if I want to be able to sum a geometric series, if it's going to be convergent, that means that R value, the absolute value of it, has to be less than 1. Notice R to the n, all I've done is replace R with x, some variable name. So if the sum of x to the n is going to equal this convergent geometric thing, x is really our R value. And for it to converge to this number, whatever this number is, whatever that sum is, for that series to converge, that means the x value, whatever that x value is, the absolute value of that x value has to be less than 1. Right? In other words, x has to be between -1 and 1. Okay? X has to be between -1 and 1. Now, this might seem like almost like a small thing, but this actually teaches us a whole lot mathematically about what series can do. We call this the radius of convergence. This is the set of numbers. This is the set of numbers for which this power series will converge to a finite sum. Again, this is the set of numbers for which this power series will converge to this finite number, whatever 1 over 1 minus x is. We call this the radius of convergence. So what we've learned is actually, hey, x to the n, that's a really easy kind of function thing, right? Think about the derivatives of that. The derivative of x to the n would be n x to the n minus 1. The power things are really easy to deal with. And as long as x is between -1 and 1, I can tell you what that sum is going to be pretty easily. In other words, I can use an infinite series to tell you a function, in which case we can say that f of x would be 1 over x, which is going to equal that series. Now, I realized up here for some reason that it should have been n equals 0, right? Sorry about that. That's my part. N equals 0 to infinity of x to the n. And essentially, we can name a function a series, and that is going to be equal to some finite thing as long as x is within certain values. I want to pause for a second because my goal here is for you to come away like feeling more confident with the fundamentals. Pause. What questions and things are on your mind right now based off that explanation? Let me know what you're thinking. What's confusing to you? What can you ask? I don't expect anyone to be masters of this right now, so please let me know. What do you think? All right, I'm going to do something, a teacher move, because the silence makes me nervous. Can you, like on a scale of 1 to 5, rate yourself based off of what I just explained here? How well do you feel like you're like understanding what I just went through? 1 to 5, 5 being the best, 1 being like have no idea Mark Walter, need to understand it a different way. Please be honest with me. And Jim and Jessica are awake. I put everybody else to sleep. Oh God. Oh, okay. Okay. All right. So, what's nice about this is where I love series stuff because it's really easy to geek out about it. Like this is mind blowing to me. 1 over 1 minus x, think about it, is a fairly actually complex function to graph. It's got a vertical asymptote. It's got horizontal asymptotes. Like that's kind of like an annoying thing to deal with graphically and in terms of think about the integral of this, right? The integral of this would be negative natural log of 1 minus x. Like it gets annoying, right? But basically what we're saying is this function, hey, I could just name it a power series. It could be 1 plus x to the first plus x squared plus x cubed plus x to the fourth. That's really cool because that power stuff is easy to do derivatives and graph and all those things, right? But it will only work within some specific radius. Now, let's look down. How can we then approximate, like this power series is really easy to see how it connects. So how can we approximate other functions using infinite series? Well, turns out that we can mathematically, this is not something we're going to take the time to prove. If we want to approximate other series or other functions with series, we can do kind of what we did earlier this year with tangent line approximations. Remember, early on in calculus, we go, okay, well, if we want to approximate some function, figure out what's going on, I have some complicated function. I could draw a tangent line to it at some point, right? I need to know that point. I could draw a tangent line to it at some point C here. To draw that tangent line, I need to know that point, f of c, and I need to know the slope, f prime of c. Well, I could get a better approximation of that. If I know the point, I know the slope, I could get a better approximation if I also knew, for example, the concavity. If I knew the second derivative, I could actually make that curve fit this a little better. And then if I knew the next derivative, the third derivative, I could make that curve because a cubic curve would kind of come up here, touch it, do that kind of thing. Make it a little better. If I took a bunch of derivatives, I could do the best I can to lay all those derivatives along this curve, and they will approximate this complicated curve, just like 1 over 1 minus x was complicated. A bunch of derivatives could approximate this curve right here pretty well within some range of x values. Just like up here, this series worked within some range of x values. I could make a series using a bunch of derivatives that would be pretty close to this curve within some range of x values, the radius of convergence. So how do we actually do that? We call these things Taylor series. Here's how we actually do that. Okay? For a Taylor series, we need to remember this one formula. Every term in a Taylor series, just like up here, our terms would be relatively easy. 1 plus x squared plus x cubed. For a general sort of function, we would need to know the nth derivative of f at the place we're trying to build our function, times x minus that place we're trying to build the function, to that n power, whatever it is, over n factorial. We always start at n equals 0. So we'll start with the 0th derivative, which is just f. X minus c to the n, which is just 1, over 0 factorial, and 0 factorial is 1. So we kind of use this formula to just repeat our steps over and over and over again. We call c is the value where this function is centered. It is basically where are we building our function around. Up here, the center was 0. And then on either side of 0, between negative 1 and 1. Let's do this process, the Taylor series process for sine of x, set x equals 0. Let's see what it looks like. This is one of a Maclaurin series. Remember, Maclaurin series is a Taylor series centered at 0 that you are supposed to have memorized, but you can always build them if you forget. Here's how we do it. I start with n equals 0. The 0th derivative, that's f of, my center is 0, so that's f of 0. My f value is sine, so the sine of 0 is 0. Then I need the first derivative of my function at 0. The derivative of sine is cosine. Plug in 0. The cosine of 0 is 1. Then I come in here, I take my second derivative of 0. So our second derivative of f at 0. Cosine. The derivative of cosine is negative sine of 0, which is 0. F triple prime of 0. Let's see, the derivative of negative sine. Derivative of negative sign will be negative cosine of 0, which will give me negative 1. Then I can do the fourth derivative at 0. The derivative of negative cosine will take me back to positive sine at 0, which is 0. And our pattern will continue. We're kind of back up to the top. We'll keep going. So you always build out these values first. We need to know that. That gives us this coefficient to kind of figure out what is our location and what is the slope, what is the concavity, what is the third derivative, fourth derivative, kind of build the shape of this graph around that place where it is centered. We built out these values, then our Taylor polynomial will look something like this. Okay. We have all of our f to the n values. So I'm going to write out the annoying looking one, and then we can make it look nice. I start with the 0th derivative. F of 0 is 0. Then you'd have x minus 0 to the 0 over 0 factorial. Notice I took my f0 value. Then I take x minus my center to the n value. I start at 0, the 0th derivative, over n factorial. Plus, I move on to f prime. Now n is 1. So f, the first derivative at 0 was 1. X minus c was 0. Now I'm in my first term, not my 0th term anymore, so it looks like that. Plus, then I move on to my second derivative, my second term, that'd be 0. X minus 0 squared over 2 factorial. Then I move to my third derivative, my third term. So minus, because notice negative, minus 1 times x minus 0 to the third power over 3 factorial. Then I move to my fourth plus, that's 0, x minus 0 to the fourth over 4 factorial plus, and so on and so forth, right? This is my Taylor polynomial. It looks ugly, so we'll clean it up. What does this mean? My Taylor polynomial. This first term goes to 0. X minus 0 to the 0 is 1. Anything to 0 is 1. 0 factorial is 1, but there's 0 there. So I'll leave it out. It goes to 0. This becomes 1 times x over 1. That's just x. Plus 0 will kill all that stuff. So it goes away. So plus, actually it's not even plus, it's now minus. This will be x cubed over 3 factorial. Sorry. Minus x cubed. Over 3 factorial. Plus 0, so that goes to 0. Oh, why did I cross that out? This one should be crossed out, 0. And think about how the pattern would continue, right? The fifth derivative would take us back to up here, right? To cosine. Because the derivative of sine will take us back to cosine. So we would end up with, if we continued this pattern, 1, but this time it would be x to the fifth over 5 factorial. You might start seeing the pattern now, right? The pattern then would be, so it looks like we're plus, minus, plus. We'll get to minus down here, right? Because we'll skip over this 0. So our fifth derivative was up here. Sixth is 0. Seventh is negative, so we end up with x 7 factorial, and so on and so forth. That's how we build a Taylor series. And what this means is that this infinite series, if this continues forever and ever and ever and ever and ever and ever, within the radius of convergence, which we won't figure out, this whole series would approximate y equals sine of x within its radius of convergence. Follows questions and things. What's really cool about these things is we can do all kinds of mathematics with them. I could then say, oh, wait. Oh, okay, so this is a small notation thing. I should have flagged. So I wrote Tn The label you use here doesn't particularly matter. There's no like standard quote unquote way to do it. I called it Tn because I was indicating that this is the infinite series. So technically this is the series, the Taylor series, because I'm letting it go on and on forever. It's kind of standard if you're going to chop it off at some place and not let it go on forever to call it P sub whatever. We're going to chop it off. If it's infinite, call it T something. If you're going to chop it off and not write the whole thing, like if I stopped at x to the 7th, I would call it P. But that's not like a hard and fast rule. Does that make sense? Okay. Yeah. So if you want to, we can plug in a number and approximate what would the sign of 0.01 be? And we can plug in 0.01 and use our polynomial to approximate what would sign of 0.01 be and stuff like that. What's cool is we could also use our Taylor series to take derivatives, right? We know that the derivative of sine is cosine, but if you actually sat here and took term by term derivatives here, you would find the Taylor series for sine. So we can take derivatives and integrate Taylor series just by looking at them and doing term by term derivatives. The derivative of this Taylor series would be 1 minus 3x squared over 3 factorial plus 5x to the 4th over 5 factorial minus 7x to the 6th over 7 factorial, and so on and so forth, which is pretty cool, right? I think it's cool. Just to explain, I include some memes on here. This man here is Roger Taylor. He was the drummer for Queen, and Ben Hardy played him in the Bohemian Rhapsody biopic, but there were people who would accidentally post instead of, they wanted to post pictures of Roger Taylor, but instead would post pictures of the actor because they got confused. Here is our general like formula again for these Taylor-Maclaurin series. All right. I want to do one more as an example, and I want you to practice some, okay? Let's find the second degree Maclaurin polynomial. So this means we go up to the second derivative. Maclaurin means centered at 0, polynomial for e to the 2x. We build out our f numbers first. We start with the 0th derivative. So f of 0 is 2 to the, when I plug in 0 up here, that'd be 2 to the 0. Then I take the derivative, f prime of x. So I take the derivative up here. What do we got to be on the lookout for the derivative of e to the 2x? Type it in. We got to look out for the derivative of e to the 2x. What derivative rule? Chain rule, exactly, e to the 2x. So derivative of e to the blah is e to the blah times the derivative of the inside, so the derivative of the exponent is 2. That means we need f prime of 0. So I plug 0 into this. That'd be e to the 0 is 1 times 2. I do my second derivative. Derivative of e to the 2x times 2. Hey, it's another chain rule thing. So e to the blah stays as e to the blah, but then I multiply by the derivative of the inside, which is 2. So 2 times 2, that constant multiple that was already there, will give us times 4. So what is f double prime of 0? I plug 0 in here. E to the 0 is 1 times 4. Now I have all my numbers. I want the second degree Maclaurin polynomial, so we can call it m sub 2, we can call it p sub 2, it doesn't really matter. I prefer just for any of these polynomials to call them p sub whatever I'm stopping at of x. So this polynomial is going to approximate e to the 2x within whatever its radius of convergence is. Okay. So how do I do that? I start with my 0th term. It's 1 times x minus 0 to the 0 over 0 factorial. So all that stuff is 1. For this first term, it's always just going to be some number. There it is. Plus, then take the first derivative, which was 2, times x minus c, where c is 0, so x minus 0, just call it x, the first power, over 1 factorial. You don't even have to write that because 1 factorial is, right? So I'm actually not even going to write that. If you want to, you can write out all the power factorial stuff. There's nothing wrong with it. It just adds extra stuff. Plus, now I moved to my second derivative. It was 4x minus 0, so I'm just going to call it x, squared over 2 factorial. There we go. Here's my second degree Taylor polynomial. I could use it to approximate, for example. I could use it to approximate. Let's just use it to approximate f of 1. See what happens f of 1. Right. Using it to approximate f of 1. 1 for x, so that'd be 1 plus, I plug in 1 up here. That'd be 2 plus, plug in 1 up here. That'd be 4 over 1 squared, right, is 1. So that's 4 times 1. That's 4 divided by 2 factorial is 2. 4 divided by 2 is 2. It turns out our approximation would be 5. Interesting. Now, let's do a quick check. How close is that approximation? E squared. Our approximation was it was 5. Turns out E squared is 7.389. Our approximation was not super close, but think for a second. That's really because we stopped our Taylor polynomial. Remember, the series is infinite. We only stopped it at the third term. So if we kept adding stuff together, this number would come up and hopefully get closer and closer to the actual value. Thoughts or questions? Seeing a second example. All right, go ahead and give practice 2 a shot. Read carefully. Make sure you're doing the derivatives well. I'm going to work on it silently so you can check yourself against me if you would like. This one we want the third degree Taylor polynomial for natural log of x, centered at x equals 1. All right, I'm going to start working it out in case you want some help. Be careful with the derivative, the second derivative, because the derivative is 1 over x, right? But we got to keep taking derivatives. 1 over x is the same thing as x to the negative 1. Let's keep that in mind. If you have questions, jump on the mic or drop me a message. Yeah. All right. Well, yeah. Let's talk about that at the end of this one. That's a good question, Jeannie. If you get done, go ahead and jump into the next practice one that's down there. All right, so this is what I got. Do be careful with your derivatives here. Your natural derivative of the natural log is 1 over x. Its derivative is negative x to the negative 2. So when x is 1, does that be negative 1? The derivative of that is positive 2 times x to the negative 3. Plug in 1, you'll get 2. We build out from there. The first term is always just that number, so it's 0. Plus the second term is 1 times x minus 1 to the first power over 1 factorial. So did write out the 1 factorial of the first power. It always looks something like this. Minus 1, x times x minus 1 squared over 2 factorial. Plus 2, x minus 1 cubed over 3 factorial. There is my third degree Taylor polynomial. Right. So Jeannie's question. Tips for finding the general term of a series. First, some series that is easier to do than others. In general, what I would recommend doing is if we're asked to find the general rule for some series is after you've written out your series here, go ahead and put underneath them as a note to yourself the n value that represents. I'm going to write in red here because actually sometimes it helps to go up to like n equals 4 or 5 to be able to see the pattern until you get really good at these. Something more hard to do, but I'm going to have another more term here. So if we think about the next term, we would take the derivative of this. It would be the next derivative would actually get us negative 6 x minus 1 to the 4th over 4 factorial. And then that term would represent n equals 4. And then this is what I like to start doing. I start with the things that are like most obvious to see how it connects with our n value and build out from there. So like n value of 2, 3, that should be n value of 4. I like to start with those because it's easier to see. So notice my n value connects with my factorial in the denominator. It also connects with my exponents. And the x minus 1 stuff is always the same. So it looks like my general series is going to look something like this. I kind of fill in what I know. I know it's going to be over n factorial. Write that in. I also know that every term here uses x minus 1 to whatever the n value is. See that? Now here's where things get a little funky. Right? We go, well, what's going on with these things here? I notice that it is alternating. 0 plus 1 minus plus minus. That gets interesting. So it's alternating. I will need some alternating thing in here. So that means I do need a negative 1 hanging out in here. Notice that if it followed this pattern, minus, positive, it looks like the starting one should be a negative, right? Should be negative. So we need, when n is 0, we need to have a negative sign in front of it. That way when n is 1, it's positive. So we need a negative 1 there, but it needs to be something like the n plus 1 power because we want the even numbered n's to be negative, and we want the odd numbered n's to be positive. This is where we start doing all that problem solving. We got to be sort of flexible problem solving mathematicians. So we can check to make sure this lines up. When n is 1, my term needs to be positive. So when n is 1, negative 1 -1 squared will be positive. That'd be x minus 1 to the n, so I get x minus 1 over n factorial, that'd be 1 factorial. So yeah, it would look like that. But I still haven't answered how I get these numbers, though. Notice this. These numbers are coming from bringing down these powers, right? My next derivative, I brought down 3. It was 3 times 2. Next time would be 4 times that, 5 times that, 6 times that. That is a cascading set of multiplication. We'd be multiplying 1 times 2 times 3 times 4 times 5 times 6 times 7 as we take derivatives. That sounds like a factorial. Notice up here, 6. That's the same thing as 3 factorial, right? 2, that's the same thing as 2 factorial. 1, that's the same thing as 1 factorial. So it looks like the coefficient here is really the n value minus 1 factorial. Now, we would have to adjust a little bit here because this first term is 0. So we might want to adjust some of these numbers and start it at 1 or whatever if you want to. But in terms of processes, that's the general way that I sort of process through it. Unfortunately, it's not like a skill that's really quick because you do have to kind of look at each situation. I do like to write my n values underneath it so I can start making those connections. Does that help, or does that cause any questions? I know that this is not quite right yet because I need to take care of that first 0 value, but that's the general process. Does that help, Jeannie? Did that help? Oh. Yeah. Okay. Sure. So let's. I'll do that. We'll add that to some of the stuff that we'll do here as we move forward. Let's do. What would be good? What would be good? Lots of different practice things we could do. Let's do. Let's walk through practice 3 together, and then I'll have you all practice. Another one, and we'll just kind of keep alternating. I'll make sure we do at least one more if it makes sense to, because not all the ways the questions are asked can we actually do the general rule. But we'll do the best we can. I'll do at least one more. All right, so practice 3, let's see what it says. We now know the general process for the Taylor polynomial creation. We just got to make sure we find the right information to do that. Function h has derivatives of all orders at x equals 0. It is known that h of 0 is 2, h prime of 0 is -1, the nth derivative at 0 is given by this formula when n is greater than or equal to 2. Write the third degree polynomial for h. Oh, that doesn't actually sound too bad. Write the polynomial. We need h of 0, which we have. It was 2. H prime of 0, which we were told was -1. To write the third degree, we would need h double prime of 0. So we go, okay, h double prime of 0. That is where I go to my formula for n is greater than 2, and now we're on the second derivative. So the second h to the 2. Not to the 2, but the second derivative of h at 0 would be 2 squared over 2 factorial. 2 squared is 4. 2 factorial is 2. This would be 2. H triple prime of 0. That means I need the third derivative, so go to my formula. That means 3 squared over 3 factorial. 3 squared is 9. 3 factorial is 3 times 2 times 1. That's 6. 9 divided by 6 give us 3 halves. So we can build our third degree Maclaurin polynomial. Piece of 3 of x would be 2. We also start with that value. Minus 1 times x minus c. We're centering it at 0, so it's just x to the first power over 1 factorial, so you don't write those things typically. Plus 2. X minus c, but c is 0, so it's just x squared over 2 factorial. Plus third derivative, that's 3 halves. X minus c, which is 0, so x third power over 3 factorial. There we go. Jeannie, this one we can't really do because we don't have, they're just kind of giving us these two numbers that don't actually fit this pattern. So it's a hypothetical situation that we can't really do something with very easily. In some ways we could start kind of building this. This would be n equals 0, n equals 1, n equals 2, n equals 3, and so on. We could at least go ahead and realize that our sum then here, the denominator, it looks like our factorial thing stays the same. That's over n factorial. That's part of the Maclaurin series rule. X to the n power. This number 3/2 came from this formula. 2 came from that formula. But unfortunately, these two things right here are just like made up numbers that they just told us. So they don't actually fit the pattern per se. So we can't really finish writing the general rule, but we do know. We could say, if we wanted to, that when n is 2, starting at n equals 2, we could then plop in here n squared over n factorial for n is 2 and above. But we can't actually write the general thing because these numbers they just gave to us. They're just like made up numbers. So I'll go back. Go ahead and try the next practice one then, one below it. Read carefully. You'll follow the same pattern of how to write Taylor polynomials. You need to know all the values and their derivatives and those values. You might have to do a little work with the table and the integral that you're given. Jeannie, does that make sense though? Why I can't really write out the real true general thing for that one? Yeah. So I'm sorry this one was not great because they just kind of threw numbers at us that don't fit the pattern. Try example 5. I want to work it out silently too if you want to check your work. Values of the derivative. Oh. Right. So I'm going to write out mine. Sorry about that. Let's see. We want the second degree Taylor polynomial for h at x equals 1. So we're going to use a lot of this x equals 1 column. So we need h of 1. H of 1 is going to be 4 plus the integral from 2 to, when x is 1, that'd be 2 to 2 of f of t. 4 plus 0. H prime of 1. Take the derivative of h derivative 4 is 0. Now, this is where we got to be really careful. Depending on where you're at, I do want you to check your work as I'm narrating this out. We need the derivative of the integral from 2 to 2x f of t dt. Now remember, in general, the derivative from some value to x of f of t dt is f of x. But notice our upper boundary this time is 2x. What do we do with that? Well, it becomes a chain rule problem. We still will plug in the upper boundary, f of 2x. We're taking the derivative of that, and that is a positive function now. So times the inside, which is 2. The derivative of this integral thing is f of 2x. We plug in the upper boundary, take the derivative. So we multiply by the derivative of that boundary. This is 2x chain derivative. Technically this is h prime of x. So what does that mean? H prime of 1 f of 2 is 0. Times 2 is 0. H double prime of x. I need the derivative of this thing now. That'd be f prime of 2x. We have it inside, so another chain rule. The derivative of the inside is 2. There's already 2 out there, so it's times 4. H prime of 1. H prime of 1 be equal to f prime of 2. So I'm plugging in 1 for x. F prime of 2 times 4. F prime of 2 is negative 1 times 4. Negative 4. So what do we get? We get here then that our Taylor polynomial second degree. Start with that value. Plus, my next term will just be 0. Times x minus 1 to the first power over 1 factorial, but this is 0, so it doesn't matter. Minus 4 x minus 1, because I'm considering it at 1. Right? Now on my second derivative, this is a squared over 2 factorial. Thoughts or questions about that? Again, Jeannie, unfortunately, this one is also not one we can write out a general rule for because they just kind of gave us random numbers. Thoughts, questions? Correct. The second derivative information up there, Alvin, yeah, is there as extra. All right, and this is why actually these kinds of questions, I would not be surprised if this kind of tabular question using a table is the kind of thing you might see. Because look at all the cool stuff it tests the student on. Do you remember how an accumulation function works? Do you know how to use a table with derivatives and things? Do you know how to take the derivative of an integral where the boundary is not just x? And do you know how to do a Taylor polynomial? Like all those questions all kind of roll in together. So this could very well be, and it's a question that a calculator doesn't really help you on. This is the kind of question definitely I think you could be ready for. Let's just do one more as practice. I've included other problems in there if you want me to check them. At 2 o'clock, I gotta go about 2 o'clock. But if you have questions about like any of the problems in here, just email me. I'll share the work with you, and you can check against them. Jeannie, to your question, Nina reminded me actually that I've recorded an explanation that I did with some students about your question. And so, would you mind instead of using this time to go through that it's on the interventions page, but I'll find it for you and email it out to everybody. Is that okay? I did a little video about finding general terms. Okay, cool. All right, let's do one more here. The function g is continuous and has derivatives of all orders at x equals -1. Hey, that sounds like we're going to have to do something at x equals -1. It is known that g of -1 is 7. And for positive values of n, the nth derivative of g at x equals -1 is defined here. So this is a little confusing. Basically what it seems like, if n is even, if we're on an even derivative, then it's 0. If we're on an odd derivative, it follows this pattern. So we want the 5th degree Taylor polynomial centered at x equals -1. Okay, so we define same process, right? G of -1. G of -1 was 7. So now think to yourself, I need the first derivative at -1. So what's the first derivative? First, that's odd. So I plug in 1. 1 squared plus 1, 2. That's my first derivative value. My second derivative value at negative 1. Second derivative, that's even. That means this value is 0. Third derivative at negative 1. Third derivative, that's odd. 3 squared plus 1 is 10. Fourth derivative at negative 1. Fourth derivative, that's even, so my derivative is 0. Fifth derivative at negative 1. That's odd. Take n squared plus 1. 5 squared, 25 plus 1 is 26. Now I write out my Taylor polynomial, 5th degree Taylor polynomial. It's going to be equal to 7. I just take that number. Plus 2 times, remember it's x minus where we're centering it, so minus negative 1. That'll be x plus 1. The first power over 1 factorial, so I won't write all that stuff. Plus 0. Plus 10 times x plus 1, whereas x minus c. C is negative 1, so it's x plus 1. This is now the third derivative term, so it's cubed over 3 factorial. I go for an extra. Oh, my fourth term is 0 plus 26 x plus 1. This is my fifth derivative, so it's 5 over 5 factorial. There we go. Now keep in mind, we've not seen many of them, but you could be asked also to use this to approximate some value. So you could plug in and say, use this to approximate g at, negative 1.1. Go ahead and plug that in. We could also be asked, give me a second. We could also be asked to take derivatives of this. And they said, hey, what is g prime of x? We could take the derivative. We approximate the derivative of g prime. We can integrate this to approximate the integral. Here's what I'd like you to do. We're going to wrap up here. Again, I will email out to everyone of the video that will help you with general term, making a general term. There's extra problems in here if you want to practice with them. I would love to have you practice and email me and have us talk about it. I do have office hours today at 3 o'clock. Join. That'd be great. I will also post the answers to AP Review 14 so that y'all can check that before you do the practice test. And that should be about it. Please make sure you've done the practice test before our class tomorrow. Please come to live classes. We're going to be going over some super important stuff. Right. Oh, I don't know what I was going to ask. Before you leave, can you go ahead and put here just as a read for me? Based off of what we did today, how did it affect your confidence and knowledge here? Put a -1 if it made you more confused. A 0 if you're like, I'm still about the same. A +1 if you felt like it boosted your knowledge. And other than that, I love you guys. Take care. Be sure you do the practice test. Follow the rules there. Plus 1,000. Oh boy. Plus 10,000. I can't even read. Cool. All right. I love you all. Take care. I got to head out here in a minute, but office hours are at 3 o'clock if you want to come by with other questions. Bye, everyone.
Thank you, Mark Walter.
Welcome.
Thank you, Mr. Mark Walter.
Yeah, say, Steven.
Yeah, what's up?
You came in late, right?
Yeah, I came in at like 1:55.
Yeah. I recorded this, and so I'll post stuff, okay?
All right, nice. All right, bye, Mr. Mark Walter.
Bye, Steven.
Also, I emailed what's it called? Dr. Mark Walter too recently too.
Sure.
So that's nice too. All right, thank you, Mr. Mark Walter. Have a nice day.
You too. Bye. Someone just sent me a question. Yes, you can work on ratio questions with me. During office hours, I know that at least there'll be a couple of people there probably. So I'll be bouncing back and forth, but that's a good time to work on ratio questions as I'm working back and forth with people and practicing. Sounds good. Bye.